Hi everyone, it's my pleasure to introduce Professor Yue Hu. Yue is an assistant professor at Operations Information Technology at Stanford Graduate School of Business. Her research lies at the intersection of healthcare operations management and applied probability, with focusing on scheduling, staffing, and patient flow management in healthcare delivery system. She studies how to leverage predictive analytics to guide operational strategies and innovations. In addition to solving these practical problems, she also conducts research in developing new methodologies for the approximation control of stochastic system. She also won a number of awards, including this APS Best Student Award and the finalist for Doing Good with Good OR competition and the IBM Best Student Paper Award, etc. So without further ado, let's welcome Yue to give us a talk today. Thanks.
Thank you so much, Sophie. Thank you for hosting me and thank you for the kind invitation. Okay, hi everyone. My name is Yue. So as Sophie kindly introduced, I'm currently an assistant professor from the Operations Information Technology group at Stanford GSB. So today I'm very excited to share one of the more recent works on online learning for dynamic service mode control. And this work is joined with several amazing collaborators, so including Wen Qian, who is currently in the audience with us. So Wen Qian is a third-year PhD candidate from Stanford MSNE. And then with two other co-authors, Anand from Amazon, and then Vahid Sarhanjian from University of Toronto. So it seems that Vahid is also in the audience with us today. Okay, so in this work, we're going to look at the very classical speed and quality trade-off in service systems. And this speed and quality trade-off is very prevalent across many diverse service systems and has been quite prevalently studied in the literature as well. So imagine in these systems, so the service provider has the agency to choose how fast he wants to spend time or serving a customer. And then the more time that the service provider spends with the customer, the higher the chance that the service quality out of the current service episode is higher. Okay, so imagine this in a common retail setting. So you may have a salesman trying to spend more time with a customer in the store, trying to increase the chance of that customer making a purchase. Okay, or in healthcare, you might also encounter a provider trying to spend more time serving or talking to a patient in hope of increasing the overall care quality for that patient out of this current service episode. Okay, so this is going to be the main service versus quality trade-off we're going to focus on. And in this work, we're going to particularly study this speed versus quality trade-off in service systems with cold start. Okay, by cold start, I mean we're going to focus on applications where this trade-off between speed versus quality is a priori unknown. Okay, in other words, so how service quality depends on the service times would be a priori unknown to the service provider. Okay, and then I'm going to give you three application examples where you will face this speed and quality trade-off from a cold start. So the first two examples come from healthcare setting. So where the first example comes from the AI-assisted provider workflow in replying to patient messages. And this is one of the practice that has been piloted by multiple hospitals across the United States within the past year. Okay, so in this example, imagine that patients will send messages to providers, and imagine these providers to be physicians or your PCPs, so your primary care providers. And these scenarios, so providers are expected to address these patient-initiate messages or inquiries, and then respond to this patient's message timely. Okay. So what has been experimented over the past year is an AI assistant workflow that allow providers to work together with a generative AI model to co-draft and refine a message before it is sent out to the patient. Now, so this screenshot I'm pasting here is one of the user interface that was adopted by one of these pilot studies. So this, you can think about this as a typical provider inbox from the provider's view. And here, so the provider opened this inbox and then is going to see one of the patient message awaiting reply. And so typically, So in the most traditional service modality, this provider would just start by drafting a response from scratch and then dispatch it to the patient. Okay. And now in this new AI-assisted service mode, the provider would instead see a richer interface. And then in this richer modality, this provider would have the option to first start by seeing a draft drafted by a generative AI model as shown here. And then the provider can iteratively work with AI to refine this draft and then dispatch it to the patient. Or alternatively, so if at times this physician would just prefer to still just draft the response from scratch, then this physician can still have the option to choose a start from blank, a reply option. So in this case, so in this pilot, the physician has the agency and autonomy to choose which mode. So either the traditional mode where the physician would just start the reply from scratch, or an AI-assisted mode where the physician would work with an AI-generated drafts and then co-refine this draft before dispatching to patient. So what the recent pilot studies have found is that this AI-assisted mode has a tendency to improve the response quality. So for example, these AI-assisted drafts tend to be more empathetic to patients. So patient satisfaction after seeing these replies tend to be higher. But at the same time, so note that we always have a physician in the loop in this service modality. And due to the time needed to monitoring the AI drafts and then iterating on the response, so the time it takes for a physician to finalize a draft before dispatching to patient tends to worsen and increase. Okay. So, and a similar AI-assisted workflow has also been examined in the radiology department. So here we are seeing a very similar workflow where radiologists can have the option to either just draft their own radiology report after seeing the patient's MRIs, or choose to work with a generative AI model to improve and refine this radiology report. And so what the recent pilot studies over the past year have found is that, so by working with these AI, so the radiologists and AI co-drafted reports tend to have higher quality in terms of diagnostic accuracy. However, at the same time, still, so working with AI would consume more time from the radiology side before finalizing a report. And in these two examples, so one may argue that so these trade-off between speed and quality could be more transient in the sense that maybe in the future, as one further fine-tune these AI models, then maybe this trade-off would vanish altogether. So there will be no disadvantage of collaborating with AI. So in the sense that both the quality and speed may improve. So that could totally happen. But my point here is not to argue that this type of trade-off will persist in the future, but just to show you examples where new service modalities would emerge as our technology keep developing. Okay, so lastly, I want to show you another example deviating away from the healthcare setting. So, and this is in a more business and marketing applications. So this is related to observation that nowadays, so with the prevalent usage and addiction of social media, so many businesses and retailing brands will start experimenting with a new type of marketing campaign. So where the marketing team of this business would contract with influencers, and then by working with influencers, they will co-develop this marketing campaign with influencers on the social media together. And so media articles have reported that, so while this type of campaign, so new campaign by cooperating with influencers, have a likelihood of increasing engagement and sales on social media, but at the same time, so the time it takes to co-produce this type of influencer marketing campaign tends to be longer due to the time it takes to contract with influencers or co-develop the contents in the marketing campaign. Okay, so all of these three applications I've talked about have witnessed this speed and quality trade-off in service systems associated with new service modalities enabled by new technologies in a cold start environment. And this is going to be the core motivation and focus of our work. And just to quickly summarize, so here we're going to focus on service systems where service quality tends to improve with the service time. And so in the aforementioned examples I talk about, let's imagine this to be so AI-assisted services in the healthcare example, or the marketing campaign by collaborating with influencers. And these type of service modalities or campaigns tend to be slower, but they tend to be more effective and are associated with higher quality revenue or sales. Okay, and in these cold start environments that we're interested in, so the rewards associated with these new service modes are both random, so meaning that so they're stochastic by nature, and more importantly, they are initially unknown to the system manager or service provider. Okay, so for example, in the AI-assisted workflows, so without experimentation, we would have a little prior on how these AI-assisted service mode, how effective these AI-assisted service mode would be. And lastly, in this type of service systems, so we care about two metrics. So we not only care about the rewards generated, so the rewards generated by these service episodes measured by sales, care quality or engagement, but we are also interested in controlling the congestion level of the system. Okay, and you can imagine this congestion penalty to be imposed by a holding cost of having customers waiting in the queue before entering service. Okay, so our goal is twofold. So we will aim to maximize the cumulative rewards collected by providing the services, and at the same time, we also want to mitigate the congestion level of the system to a reasonable level. Okay, so overall, our research question is to optimally learn and control service modes to maximize the long-run net rewards, and when the reward distributions are a priori unknown. And this is going to be the overarching goal of this work. So before I go talking about solving this research question, so let me first talk from a high level of the three streams of literature our work is mostly related to. So our work is related to three streams of literature, and the first comes from the dynamic service rate control. And you can imagine this to be the stream of literature that studies the optimal dynamic service mode control problem in a full information setting, so where everything is known. And then now after introducing unknown parameters, so our work is also related to literature that combines online learning in a queuing setting. And you can imagine, so I would want to point out that we are one of the first to look at the dynamic service control problem with unknown reward distributions. Okay, and lastly, so from a more high level, so our work is related to reinforcement learning literature for unbounded state MDPs. Okay, so now let me go into introducing our model. So in this work, we're going to consider a Markovian queuing system with two service modes. Okay, so the service provider can choose at any time to serve customers in either what we call a premium service mode or a basic service mode. Okay, and here, so the premium service modes, you can imagine this to be associated with longer service time, but higher service quality. And so here I'm going to use mu p to denote the service rate of the premium service mode, and then RP to denote the reward associated, the average reward associated with applying this premium service mode. And at the same time, the service provider can also choose to adopt a basic service mode. And so this basic service mode is associated with service rate mu b, and then an average reward rate RB. So our model, our analysis will not require any prior assumptions on how these service rate parameters and reward parameters order. But for the applications of interest, you may imagine, so for intuitive interpretation, you may imagine that the premium service mode is of higher quality. So the R, the reward value for premium service, will be higher than that of the basic service. And in compensation, the premium service mode tends to be associated with a slower service rate than the basic service rate. And so we're also going to assume that, when the customers are waiting in the queue, they also incur a unit time holding cost at the rate C per unit time. And so our control, so the policy that we're interested is a state-dependent policy that maps the current state of the system, which is the current queue length, to a type of service mode that the service provider chooses. And so throughout this work, we're going to assume preemptive services. Okay, and then our goal is to choose the optimal service mode control to maximize the long run average net rewards. And so these net rewards would first combine the cumulative rewards that we've collected by providing services up to time t, and then minus the penalty of system congestion. And so here we're subtracting the cumulative holding costs by holding customers in the queue. And our goal is to find an optimal service mode policy that maximizes the long run average of the net rewards. And so here you can, so let me just reiterate on the inherent trade-off that we are facing between system congestion and rewards. So you can imagine two very extreme service policies where, so one extreme policy is that you would just utilize the premium service mode all the time. And recall that the premium service mode is associated with a higher reward rate. So here, in this case, you max out on the rate of collecting rewards. But it's at the same time, because premium service modes tend to be slower, so you're also maxing out on the accumulated holding cost penalized by congestion. And to the other extreme, you can also imagine that, so if we just simply utilize the basic service mode all the time, then here, well, we potentially face the minimum level of system congestion and holding cost, but we're also missing out a lot on the rewards. So that's going to be the main problem we're interested in. So to tackle this problem, so we're going to first consider this problem in a full information setting, so where everything is known. So we're going to characterize the optimal full information policy, and then we're going to show that, so this optimal policy in a full information setting, so assuming that we know all the system parameters, is of a threshold type. So what do I mean by threshold type? So I mean that there is going to exist a threshold, an optimal threshold Q star, such that, so the system manager should apply the basic service mode when the system is congested. So the faster service mode when the system is congested, and when the current number in the queue is above this threshold Q star, and then only apply the premium or slower service mode when the system is lightly loaded. So when the current number in system or number in the queue length is below this threshold Q star. And so as I mentioned, so this full information dynamic service rate control problem has been prevalently studied by the literature. So, and this proposition, so we mainly just derive this for our problem setting by adapting existing results. Okay, and we also, so there's also a quite straightforward way to compute this optimal offline, so full information threshold Q star, which is just simply by just writing out the section distribution and balance equations, and then we'll be able to express a objective function, which I call the value function, which depends on a threshold that you give, and then all the other system parameters, and then you can just find the optimal threshold, so Q star, that maximizes the steady state objective value, so val Q. And this is a way to just compute the optimal threshold Q star from the value function. And now let me just introduce, let me just show you two instances on how the val Q function, so the value function behave. So we're able to show that this value function, assuming that you know, so in the full information setting, is unimodular, but lacks global concavity property with respect to the threshold. And so here, so this unimodular property is also going to help us to derive more structural results in the online setting. So where we do not know the service the service reward distribution a priori. So this is what we found in the full information setting. And now, so taken the optimal policy we've characterized in the full information setting. So what I'm going to move on to is an online learning setting where we don't know the mean reward or reward distributions a priori. And our goal is to learn this optimal threshold policy that we have characterized in the full information setting just by observing the empirical estimates in a data-driven manner for the service rewards. Okay, so and then the benchmark for our online learning algorithm we're going to propose is going to be this cumulative regret defined as the difference between two quantities. So here we're going to first benchmark against this OPT quantity, which is the optimal steady state objective value in the full information setting. Okay, so this is OPT is going to be the optimal steady state value generated by my optimal threshold policy in the offline setting. And then we're going to compare, we're going to compare our empirical performance under any proposed policy pi. So where we include both the cumulative rewards and also penalize for system congestion in holding cost. So we're going to compare the empirical performance of any proposed policy pi against this OPT benchmark. So this is our main objective, which is a cumulative regret of our policy. And at the same time, so we are also able to just alternatively look at another type of regret definition. So where instead of just benchmarking against this static OPT value for all t time units, as I defined above, but instead we're just going to apply the optimal threshold policy that we derived in the offline setting, so this pi star, just to the transient dynamics too. So in this non-stationary regret that I defined here, so we dynamically apply this optimal threshold policy in the offline setting to the transient system dynamics. And then we're going to compare our performance, so empirical performance of the proposed policy pi with this optimal transient dynamics under the policy pi star. So where again, pi star is the optimal threshold policy that we derived in the full information setting. So we're going to, so all the future analysis would apply simultaneously to both regret definitions that I'm showing you here. Okay, so having introduced our regret definitions, so what I'm going to do next is to introduce a policy that we propose, so which is what we call an episodic UCB algorithm. So in the online setting, what we're going to do is to apply, it's going to apply this algorithm. So where this algorithm takes, all of the known system parameters as input, okay? And then we're going to initiate, so we're also going to introduce and compute what we call an approximate upper bound Q bar on the optimal threshold. So let's recall that our goal is to learn the optimal threshold Q star that we computed from the full information setting. But then the exploration space would be countably infinite because I have all the positive integer values that I will be able to explore. So to make exploration more tractable, we introduce and compute what we call this approximate upper bound Q bar. So what the algorithm will do next is just to restrict the search space from the countably infinite horizon to just from 0 to up to this upper bound Q bar. And our analysis is going to show that our definition of this Q bar is good enough. So by approximate upper bound, I mean, so there are certain scenarios, so this Q bar would just be a perfect upper bound, will be an exact upper bound on Q star. And there are other scenarios that this Q bar will not be an exact upper bound, but it is good enough, meaning that it's sufficiently close to the Q star that we want to approach to. Okay, so this is what I mean by approximate. And this Q bar is going to be very crucial for defining our episodic UCB algorithm. Okay, so now having read in all the known system parameters, and then having also introduced this approximate upper bound Q bar, So what I would do next is to initialize the system with a threshold policy and with just any, with any threshold policy. So for now, I'm just going to assume that I'm just going to apply a threshold equal to 1. And then I'm going to operate the system. So I'm going to operate the queuing process in episodes. So by episodes, I mean, I'm going to look at episodes defined by the, the 2 consecutive heating times of 0 of the queue length process. So each episode would start with Q equal to 0, and then would end after my queue length process hits 0 again. So my episode essentially is an entire busy cycle of the queue length process. Okay, so then in each episode, we're going to do the following. So we're going to deploy our current threshold policy. So with threshold given by this queue head, and then I'm going to collect samples. Okay, so within each episode, I'm going to collect samples from my premium service modes, and then I'm also going to collect samples under my basic service modes. And recall that I will be able to collect premium samples, so premium service samples, if my queue length process exceeds, falls below this threshold queue head in the busy cycle. And then vice versa. So I will be able to collect basic service samples if my queue length fluctuates above the defined threshold, so the deployed threshold within the current busy cycle. And then with using these collected samples, I'm going to update my empirical estimates for the mean rewards, so the RP for premium surveys, and then so the head RB for basic surveys. And then I'm going to, at the end of the episode, so at the end of the busy cycle, I'm going to update my threshold estimate. So I'm going to update Q head, which is going to be the threshold that's going to be deployed in my next busy cycle or episode. And then, so here, I'm not just using the empirical estimates R heads, but I'm also inserting a UCB factor for forced acceleration here. So this is my episodic UCB algorithm. Okay, so what we're going to show is under very standard assumptions on the reward distributions. So the regret of our episodic UCB algorithm is upper bounded by the order of square root t. Okay, and in our analysis, our regret analysis is centered around a novel regret decomposition that's centered around these regenerative cycles that I introduced earlier. So because in our algorithm, our episode is governed by the busy cycles, and each busy cycle is going to be a regeneration cycle for the queue length process. And our regret analysis essentially centers around that busy cycle approach and the decompositions werein. And in particular, so as I'm demonstrating here, but there is no need to go into the mathematical details. So our regret decomposition essentially consists of 4 components. So where we have a term called transient regret and another term called learning regret. And we simultaneously also have what we call residual error and approximation error. So now, in the next couple of slides, I'm going to very quickly introduce the idea behind the construction of these 4 regret and error terms. So first, so consider any simple episode case, which is the case busy cycle of my queue length process under the UCB algorithm. So the first term that I showed you on the previous slide is called the transient regret. And so this transient regret captures the discrepancy between the system's transient behavior and its steady state performance. And in episode K, you can just imagine this term to be captured by the following quantity. So it measures the distance between, my value function, my true steady state objective value evaluated by adopting, the current threshold deployed in the current episode, Q head K. And then I'm going to compare, so this is the true steady state performance utilizing this current threshold. And then I'm going to compare it to my current performance. So in my transient system dynamics, so in the case episode. So I'm going to look at the performance in my case episode and then compare it to the true steady state value. And so for those who are familiar with analyzing this type of transient regret in an online learning and queuing setting, So this type of transient regret, quantifying the distance between the system transient dynamics and the steady state behavior, can be notoriously hard to deal with. But here, another thing to note is, we're deploying a novel regret decomposition where we're operating the UCB algorithm over regenerative cycles defined by the busy cycles when my Q length hits 0 consecutively. So, and within a regenerative cycle, so what we're able to leverage is that, so due to the renewal reward theories, so just by construction, the transient regret we're going to incur in each episode is exactly 0, meaning that because each episode is a perfect regeneration cycle, which is also a busy cycle in the current Q-length process. So here, the transient regret term is just exactly 0 because the expected performance of my current episode K under my proposed policy is just going to be exactly equal the expected steady state performance. So this is my transient regret. And the next important regret term is called the learning regret. And this is the cost that we incur by not knowing a priori the model parameters. So this is the cost that we would incur by progressively acquiring information of the unknown reward distribution parameters. And in the current episode K, you can imagine this to be, suppose that we compare my full information setting with my online learning setting, and then I'm just going to optimize my value function over the same range. So by the same range, I mean, we're going to optimize value function over the interval from 0 to my approximate upper bound Q bar. And then what is the gap from here? So if we know everything, then we would incur no gap here. And so this gap here is essentially driven by the fact of us not knowing the mean reward parameters a priori. And what we are going to show is that, so this learning regret consists of the bulk of our regret. And this order is at the order of square root t. And so this is the learning regret. And next, so as I mentioned earlier, so we also had, so because our algorithm is operating with an approximate upper bound Q bar, whereas the Chu problem would face a completely infinite search space where you should search the threshold value from 0 to any positive integer values. So here is the approximation that we're doing in the algorithm by imposing that approximate upper bound Q bar, we call it an approximation error. And because I also mentioned earlier, so our construction of Q bar is effective in the sense that, so there are certain scenarios where the Q bar will just be a perfect upper bound on Q star. And there are other scenarios where this Q bar is good enough. So this is what I mean by good enough. So I mean that the approximation error introduced by imposing that arbitrary upper bound Q bar for the search space is just constant, so it's minimal. And this is our approximation error. And the last term is very simple, so which we call the residual error. So this is simply a cost that we incur in the last episode, where because the time horizon just ended, and then so in the last episode we may have an incomplete or imperfect regeneration cycle or busy cycle, and so this. But then that gap or that cost is naturally just constant. So it's very minimal too. Okay, so this is overall our regret decomposition for the UCB algorithm. So having introduced this UCB algorithm, I want to just recapitulate what we've done so far. So,
sorry, can I ask a question? So is this decompositions of the episode really important? Can I just decouple like every log t or like square root t as one episode, and then should you deal the same regret?
Yes, Sophie, that's a very good question. So you can decompose however you want, but you have to make sure that you're decomposing over regenerative cycles of the Q-length process. So here, what we show is that, so the time between two consecutive heating time of Q-length heating 0 is a regeneration cycle. So it's a well-defined regeneration cycle. And then we'll be able to obtain observations under both service modalities within the regeneration cycle. So as long as you decompose along that line, I think the analysis could go through. But you cannot, I think it wouldn't work if you just arbitrarily fix the time. So fix the time of each episode. So instead, so this episode should be defined by the state of the system. So I think, so that's very important. So the importance of that is that, so by decomposing over episodes, so that each form a well-defined regenerative cycle, so you will always have zero transient regret in this term. Whereas in comparison, if we just arbitrarily fix the cycle length to be a predetermined time without looking at the state of the system, so we probably will not have a perfect regeneration cycle. So the transient regret could be very nasty here. Yeah, but that's a very good question.
Thanks a lot.
Yes.
I also have a question.
Yes.
So when the queue, for example, is in heavy traffic, then this regenerative cycles could be really, really long.
Yeah, exactly.
And so this may not be good in practice, right? If we do it like this.
Yes, totally. So maybe just, so far so that's a totally valid observation. So currently, so all that I'm doing is just with the exact analysis of one single queuing system, and that is finite, and then I'm not pushing it to heavy traffic, but you're totally right. So in systems, so even in a finite system whose traffic tend to be higher, then the time for me to hit zero again could be arbitrarily long. So maybe what I'm going to introduce in the next slide, so I'm going to introduce some other algorithms that can potentially just mitigate that concern. Okay, so what I want to talk about next is what we've done so far is to combine this online learning of the optimal queue length threshold in a queuing system with two service modalities. And what I want to emphasize is that, so the complexity here introduced by learning in a queuing system is twofold. So first of all, you can imagine that the sampling frequency here the sampling frequency here in a queuing system can be much more complicated because how you sample needs to abide by the system dynamics. So just as Sushil just mentioned, so now if your system tends to operate in heavy traffic, then each episode will just tend to operate longer because you just cannot hit zero in a relatively fast manner. So how you sample, it needs to abide by the queuing dynamics, and that could introduce one fundamental layer of complexity. But on the other hand, so maybe your queuing dynamics would drive your would also facilitate sampling due to some free exploration property. And this is what we're going to explore next. Okay, so what we're going to show that, so if some prior knowledge about the system is known a priori, so in the sense that first, so if a priori, we already know that the optimal threshold to adopt in the full information setting is larger than 1, strictly larger than 1. And if the system's parameter is also in what we call a non-degenerative case. So non-degenerative, I just mean that so the trade-off between speed and quality does not vanish. So you don't have equal service rates and you don't have zero holding cost. Okay, so if we happen to have the luxury to operate under the knowledge of these two information, then using the UCB I just described above could be an overkill. So what I mean by that is, so this prior knowledge would already allow us to implement a much simpler policy of what we call episodic greedy algorithm. So this episodic greedy algorithm essentially is the same as the previous UCB algorithm. It's just in the last step. So it still operates in episodes governed by the regenerative cycles or the busy cycles of the queue length process, but only that at the end. So here, at the end of each episode, I'm going to calculate an updated guess of my threshold queue head by just using my empirical estimates of the mean rewards and without imposing forced acceleration. So without UCB factors that enforces acceleration. So this is very simple. This is just a greedy algorithm that operates in these episodes. So what we can show is, so this greedy algorithm would perform, okay, what we can show is that this greedy algorithm will perform very effectively if we have the luxury to know these knowledge a priori. And the reason it's effective is because what we're going to show is that it actually benefits from what we call a free acceleration property, thanks to the queuing dynamics, specifically in this case. Okay, so what I mean by free acceleration is that by free acceleration, I mean that even operating under the greedy policy, we are still guaranteed to have we're still guaranteed to sample from both service modes in each episode. And in particular, this means that we can observe at least one reward sample from each service mode in any episode with positive probability. So this is a free acceleration property that's going to arise. So if we have the prior knowledge on Q star, and if we also operate in the non-degenerative regime, so where we face real speed and quality trade-off. Okay, so if we operate under that scenario circumstance, then what we show is that so this prior knowledge and that specific parameter regime would help us expedite learning and just makes explicit exploration redundant. Okay, and moreover, so this episodic greedy algorithm, so building upon this prior knowledge, so conditioning on this prior knowledge of Q star, then this episodic greedy algorithm would be able to achieve constant regret. Okay, but I also want to make a quick stop here and just highlighting that. So remember that the UCB algorithm that we introduced achieved square root T regret. And so there is no inconsistency here. And because what we just established earlier with the UCB algorithm is that, so it's going to operate, well, universally for all instances without any prior knowledge on the optimal threshold Q star. So without that information, and across all parameter regimes, so UCB is able to achieve square root T regret. And only if you condition on this prior information about Q star, you will have effective greedy algorithm, and then this greedy algorithm will be guaranteed to achieve constant regret. So that's the difference here. So the greedy is operating with some prior information. So the greedy cheats in some way by assuming prior information on Q star itself. Okay, so now having observed this free acceleration property and established this effectiveness of the simple greedy algorithm within this, so conditioning on this extra information of Q star. So one natural question that arises is whether or not we can just determine this Q star, whether this Q star is larger than 1 in a data-driven manner. So what I'm curious to know is, so I've talked about the UCB algorithm that performs universally well and achieves square root T regret for all constants without any prior knowledge, but the UCB algorithm explores all the time. On the other hand, I have another extreme. So I have the greedy algorithm that has zero exploration. And then that's just going to leverage the free acceleration property thanks to the queuing dynamics, as well as some prior information on the fact that Q star is larger than 1. Then I'm curious if there is a mid ground. So by mid ground, I mean, so is there a way for me to learn or determine whether this relationship that Q star is larger than 1 holds in a data-driven manner? So it turns out we're able to close this loop by proposing another alternative algorithm that sits in the middle. So that is what we call the explore and then commit algorithm. So this explore and then commit algorithm, I don't want to spend too much time here, but essentially what it does is, so still we assume that we are in this non-degenerative parameter regime, okay? And then, but we don't a priori know whether Q star is larger than 1. And that's what we want to determine. And we're going to explore. So we're going to keep exploring just under, by deploying a fixed threshold policy, just assuming, for example, the threshold is equal to 2. So we're just going to keep exploring under this fixed threshold policy. And then I'm still just operating this algorithm in episodes. Okay? And then in each episode, I'm going to collect samples for me to draw a statistical conclusion on whether or not Q star is equal to 1. Okay, so once I have achieved sufficient statistical confidence, I'm going to commit. So either that I'm going to commit that, so Q star is actually equal to 1. So I would just be able to commit to the threshold policy with an updated threshold now equal set to 1. Okay, moving forward. Or alternatively, so I'm going to just conclude that Q star should better be larger than 1. And so in that case, I can go back and then deploy my episodic greedy algorithm I introduced earlier. So this explore and then commit algorithm are able to show that it is able to achieve an instant dependent regret bound of this much. And so note that here, so this is instant dependent in the sense that so this depends on this delta, and this delta is going to be, so it's defined as the true value for this quantity over here for the underlying system parameters, which we don't a priori know. And so note that this is also not a worst case regret bound of square root t as what we established for UCB. And so you can imagine this explore and then commit algorithm as a mid ground that sits in the middle. That's just, so it does certain exploration in the initial phase and then commit to a deterministic policy from then on without any exploration. So we've covered the whole extreme. So we've talked about the UCB algorithm that works well for all. And then on the other extreme, we have the greedy algorithm that assumes a strong prior on the optimal threshold policy. But under that prior and specific parameter regime, on the non-degenerate parameter regime, this episodic greedy this episodic greedy algorithm performs extremely well. But maybe the assumption on the prior knowledge of Q star would be too strong to assume a priori. So we can make that determination statistically in a data-driven manner. And so that would give rise to this mid ground. So this explore and then commit algorithm. But the loss is that, so here for this algorithm, it's still, so the regret guarantee is provided in a piecemeal manner. So this is instant dependent. Okay, so that is the 3 algorithms that we've covered in our analysis. Okay, and then in the last 10 minutes, I want to show you by a case study where we numerically adopt our proposed policy to the real world data. So the case study that I'm going to focus on is related to the very first healthcare example that I introduced. So where physicians were provided with the opportunity to work with AI to reply to patient inquiries. Okay, and so we're going to leverage the statistics and data reported in this medical paper to calibrate our model. And so in our calibration, what we found is, so now in this case, imagine that there are 2 service modes. So the first service mode, the premium service mode, would be correlated with, would relate to the scenario where physicians work with AI to draft a response. Okay, so that's the premium service mode. And then the basic service mode will correspond to the very traditional mode where physicians would just draft the patient message replies from scratch. So the 2 service modes. And using the statistics reported in this medical paper, so what we found is, so the service quality, so which would correspond to the RPs and RBs in the model. So the service quality would be lower in the manual or basic service mode, so 3.38, and then would be higher in the premium service mode, so which is the AI-assisted service mode. And then this difference is statistically significant as reported in the paper. Okay. And then, so this is the service quality. And then, so in comparison to service quality, we can also calibrate the service rates. And in particular, so using the statistics reported in that paper, so what we found is, so we calibrate our model to have mu b, so the service rate related to the basic service mode, so the manual service mode is faster than the premium service mode. And then, so we manually set the holding cost to be 0.01. And so this holding cost will give us a nice trade-off between quality and efficiency in the numerics. And then sensitivity analysis around the magnitude of holding cost reveals that our insights will stay robust across a wide range of values. So the particular value of holding cost here is not significant. Okay. So what I'm going to compare is to compare our episodic UCB algorithm with 3 baseline policies. So the first baseline policy is what we call an event-based UCB. So this is essentially our UCB algorithm, but then we're going to update the policy, and in particular, update the threshold that we're going to deploy in near real time. So after each sample collection, we're going to make a policy update. And this is in comparison to our episodic UCB, where you'll only do policy update at the very end of each episode. And so this event-based UCB updates policy in a much faster manner. And you can think about this as maybe providing some upper bound in performance our episodic UCB will not be able to achieve. Okay, so this is the event-based UCB. And next, we compare to a second baseline called the static policy UCB. And so this is another benchmark where we demonstrate the value of deploying a dynamic state-dependent policy, because the static UCB would just aim to learn the optimal static policy. So utilizing the very similar learning technique as what we established earlier in our work. So this is a static UCB. And then lastly, we're also going to compare to an episodic greedy policy, so which is the greedy policy that we introduced earlier, and this operates well if Q star is strictly larger than 1. And so here in these cases that we've examined, so in this particular case study, what we computed is that the actual Q star is between 10 and 20. Okay, so we indeed have Q star larger than 1. So episodic greedy is expected to perform just as well. Okay, so then as you see from these plots that I'm showing you here, so with a comparison among all the 4 policies, so what we found is that so the event-based UCB that just updates in almost near real time, much faster than our episodic UCB, indeed gives a lower bound of performance. Okay, and then next, so we have the cumulative regret given by our episodic-based UCB in green here, and which is very similar to the performance of the episodic greedy algorithm. So the greedy and UCB performance is very similar in the case study. And next, so the static UCB policy aims to learn the optimal static policy, which is either to use only the basic service mode all the time, or only adopt the premium service mode all the time. And this would also naturally give an upper bound on the regret. Okay, so this is, and so here we operate the time horizon up to t equal to 600, which is very similar to the time horizon adopted in those real-world pilot studies. Okay, and then what we found is that so overall, so by adopting our proposed policies, so either episodic UCB or episodic greedy algorithm, we'll be able to achieve about 12% to 25% performance improvement over these benchmark policies at approximately the same time, with approximately the same time horizon as those deployed in the pilot studies. Okay, so now, so let me summarize. So in this work, we consider the problem of dynamic service mode control in queuing systems with unknown reward distributions. And so here we're going to develop, so we developed online learning framework with 3 different online learning algorithms, and all of them have statistically near optimal regret bound, depending on the operating regimes and whether or not we have prior knowledge on the optimal threshold. Okay, and then in our analysis, so we develop a novel regret decomposition. So that centers around this regenerative cycle-based framework that just allow us to decompose the regret into the 4 terms that I introduced earlier. Okay, so we established conditions under which the queuing dynamics would facilitate learning through a free acceleration property. And under this property, so even greedy algorithms will perform really well. Although, so this free acceleration is only salient under an extra prior knowledge about the optimal threshold Q star. Okay, and lastly, we demonstrate the application value of our proposed policy to a case study on AI-assisted patient messaging, and then demonstrate up to about 17% to 25% improvement over the baseline policies. Okay, so with that, I would like to conclude my talk today. Thank you so much for being here, and I'm happy to answer any questions.
Thank you, Yue, for the great presentation. I think Susho, you have a question, right?
Yes, I have a question. Yes. So I'm a bit confused about the simulation results.
Mhm.
Seems like just doing UCB all the time, like not doing episodic, seems to perform well. Is that correct?
Oh, so this UCB, event-based UCB, is intended to be a lower bound for our policy. So this event UCB is when you would just update policy all the time. So
Okay.
yeah, so our episodic UCB would update policy at the end of each episode. But in event-based UCB, we're going to assume that so after every sample collection, you can do a policy update. So you update in almost near real time every step of the way, and that's very computationally expensive.
Oh, I see. That's the problem. Okay.
Yeah,
Okay.
so
You
that
don't.
is the
Okay.
problem. But yeah, so this is intended to provide. So this is intended to provide a lower bound in the regret to our episodic UCB. So this is intended to do well by construction.
And how much is the runtime difference between the two policies?
Okay, so that's a good one. So that I will need to ask our student Wen Jian, about who is also on this talk. So I'm not too sure about the runtime exactly.
Yeah.
But that sorry, go on. Yes.
I just gave like the runtime is about like it depends on like the also depends on like the arrival traffic queues, but it's nearly about like 10 times I would say.
Okay. Okay.
Thanks,
Thanks.
Yeah.
I had one more question. I think
Okay.
other people also have questions. But maybe I'll quickly ask. Sorry. So we briefly talked about this, right? That the a regenerative cycle could be too long, essentially, when your traffic is high.
Exactly.
Maybe do you think it would be interesting to truncate if the regenerative cycle becomes too long? In the sense that you let it run for the regenerative cycle, but if it becomes too long, you truncate. So essentially you are doing a minimum between this regenerative cycle and a mixing time, because if you have like a finite state Markov chain, it could mix faster than, for example, hitting 0 again, because you have a finite state Markov chain.
Yes, I think that's a very nice idea. So I think numerically, you could actually demonstrate effective performance. So as long as you've collected samples and you can update your Q threshold in a meaningful way, I think with a forced truncation, with a forced truncation when the current episode is too long, so I think maybe numerically that'll be effective. Maybe that'll be effective. Although I would like to say that so even after your truncation, your next episode may operate with a different threshold, but still with the same initial condition, which tends to be very high, right? So if you actually truncate, then maybe the initial condition for the next episode is still very high because you cannot reinitialize the system. So maybe numerically it will still be, so that type of approach will still be effective for the overall learning efficacy. But yeah, but not sure how.
So remember, you decompose the regret into 4 parts, right? The last part is if you have an incomplete cycles, right? And you have the regret is an order of square root t or something.
So the incomplete cycle only at the very end of this time horizon. So there's only one such incomplete cycle.
That is O1 or square root t. Could you remember?
O1. That's just
O1.
one cycle.
Okay.
So it's just fine.
Yeah.
Yeah, but yeah, so Shield's idea, yeah, we can think about it. So maybe a forced truncation, and we can certainly explore it numerically to see if that's effective for heavy loaded systems. Yeah, but that's a very nice idea.
So you do have assumptions on lambda is actually smaller than mu b, right? And
yes,
I think that's your assumption for.
Yeah, so our assumption is that the system is stabilizable. So it's stabilizable. So as long as there is some service mode that can stabilize the system, then we're fine. And then the sufficient condition is just that lambda is less than mu b. So mu b is the faster mode. So as long as it can stabilize the system, then we are fine.
Right. I think Yue Yang and Yue Cheng both have questions. Yeah. Sorry. Yeah.
Very nice talk, yeah.
Oh, very
A
nice.
related question. So, I think it's related to Sushiel's question. So I'm wondering, what is the length of the regeneration cycle, or in other words, how fast is the convergence rate of the queuing system?
Yeah, so that's a good question. So that, okay, maybe Wenqian can talk more about that. So that depends on the specific instances that we're testing. And in general, I think what Wenqian said earlier is,
Is
yeah,
that
so
like a
I don't
exponential
really.
convergence, or?
Oh, so theoretically, it's exponential mixing times.
Exponential mixing time. So you can prove exponential mixing time without any exogenous assumptions
Yeah.
about mixing time. Okay. So
Yeah.
so the only assumption that you relied on is mu b greater than lambda.
Yeah, exactly.
Awesome. Okay, cool. And another question is related to the maybe the structural result of the val function. So intuitively, I thought if Rp being greater than Rb would lead to a larger optimal Q star. Intuitively. So basically, if the premium service reward is much larger than the basic service reward, and then we should be able to tolerate a larger threshold Q.
Yes.
Okay, so
Yeah,
if
I think
that's the
the correct.
case, so in the UCB algorithm, because you add a UCB term plus a square root of some term, exploration term for both RP and RB. So would that make sense to have a plus square root for RP, but minus square root of that term for RB?
Interesting. So maybe, yeah, so that could be a very nice idea. So maybe we could, so the current, so the current factors that we impose in the UCB algorithms would work just fine. But then maybe, as you suggested, there could be better refinements for those, for directions of exploration, just leveraging that observation. So maybe that's, that could work. Yeah, we'll think more about that.
Yeah, maybe it doesn't improve the order of T, but maybe other dependence on the other factors.
Numerically, maybe numerically it'll demonstrate stronger performance or faster convergence for sure.
Okay, great.
Yeah,
Thank you.
I think there Xu Chuang, you have question, right?
Yeah, I just have a very short question. Given the experimental result, we saw that the event-based UCB has a better performance than the episodic-based. Could it be possible that it's because the threshold policy may not be the exactly optimal policy in a finite time horizon? I know that in the infinite time horizon, when t goes to infinity, definitely the threshold should be optimal.
Yes.
But when the time is finite, maybe at the beginning I should be conservative. And
Could
when
be.
I'm approaching to the end, I should like slightly have a higher threshold or lower threshold to use a high quality server.
Yes.
Also that the event-based UCB, because they can adapt to the time horizon, because they can change their threshold more frequently, and therefore it has a better empirical performance than the episodic based UCB. But just one potential comment.
So I would say, I think that's a very good point. So if your T is just finite, if we're just looking at finite time horizons, so currently we don't really characterize what is the true exact optimal policy, even in the full information setting. So it could just be that how you suggested, that it's not a single threshold policy. So it's maybe some more sophisticated policy that also depends on capital T itself. So that's all possible. So that we don't we haven't really characterized. But even in that regard, so event-based UCB could just be, as you said, because it's updating more frequently. So it's just updating the threshold more frequently. Although although it's still updating to the best estimate, so the best form possible to the single optimal threshold. So although it's still updating in that direction, but maybe it's still effective. But then the true optimal transient dynamics are very hard to analyze, and which we don't a priori know.
Oh, I got it. Thank you.
Yeah.
That's clear.
Mohammed, do you have a question?
Yes. Thank you very much for the nice talk. My question is, I'm wondering if there is a lower bound on the quality on the regret when Q is equal to 1. I'm wondering if it's possible to get like constant regret even in the case of Q
Okay.
equal to 1.
Very good. Thanks, Mohammed, for the question. So what we show is, so in general, so without any prior knowledge, then we can have instances. So we can establish that. So there are worst case instances where the regret would just be lower bounded by square root t. And then, so after we have, so conditioning on the extra knowledge about Q star. So if we have this extra prior knowledge on Q star being larger than 1, greedy policy can achieve order 1. So in this case, so with this under this additional information, so the lower bound of regret must be constant too. So that's the lower bounds in the two cases.
Okay, great. Thank you.
Yeah, thanks for the question.
I have a last question.
Yes.
I'm waiting. So how did you compute the Q bar? That's
Yeah, good. So Q bar, we basically constructed by just by extensively analyzing the value function. So we characterize value function in some way, and then we just and then we're looking for upper bounds for Q star through the structure of the value function. So that's essentially how we do that. But then the actual definition of Q bar is more mechanical and case dependent, as we provide in the paper. Yeah,
Okay,
but essentially Q bar is obtained by just studying the value function.
got it.
Yeah.
Okay. Okay, I see. Because I was about to ask, why don't you update Q bar over time? But then I realized it doesn't matter because
Right.
it's only 0.1 regret in terms of that part. So
Yeah, exactly.